In this section, we're going to talk about, in this video, we're going to talk about accuracy, error, and uncertainty. So, an example of accuracy is the closeness of a measurement to its true value. So that's represented by a dartboard with everything hitting the bullseye. All right. You can have consistent results within a measurement, but if there's some systematic uncertainty, you might be away from the actual value that you're trying to measure. Right. Now, if you have high random error, you don't get any consistency within your results, and you might not be able to accurately determine the true value due to that high amount of random error. Okay. So for error we define as the difference between what the value that we're measuring and the true value of the object or the thing that we're trying to the thing that we're trying to measure. Right. So a percent error is equal is what often referred to as the relative error. When we take the error and we divide by the true value and multiply by 100. Right. So the again, we defined random error as the random variation within the measurement. So in this chart here, we took different measurements, 10 different measurements, all right, and if we averaged all those measurements, this would be our measured value is the dotted line, all right. But if there was an error in how we were taking our measurements, that would give us a systematic error that would be the difference between our measured average and our true known value. All right. So, so later in the course, we're going to talk about what's just the difference between statistical variation and uncertainty. So, uncertainty is the numerical estimate of the range and error within a reported variable. So this is a function of the sources of error within an experiment. So typically, the system calibration, data set size, and the technique being used to measure the dependent variable. So, we're going to talk about these later on in future lectures. All right, and we're going to talk a little bit about the errors associated with calibration. So we're going to talk about sequential testing and random testing. So what a sequential test is when you slowly increase or decrease the input value over the full input range. Okay, the measured value that you get is the output of the test. So oftentimes during calibration, people will do sequential tests. They'll slowly increase the temperature, increase the load on a device, measure the signal, and then they'll decrease the load. That's a sequential test. The other example is a random test. Right. So a random test is given by placing all the input values in a random order. And the point of that is to try to break up effects of interference, hysteresis, or any types of observation error. So from a random test, one can identify a bunch of different additional errors. All right, but before we talk about those additional errors, we want to talk about hysteresis. So hysteresis refers to the difference in values between the upscale sequential measurement and a downscale sequential measurement. So when, let's say, you're increasing the input value, you get a different range of output value. So for the same input value, when you're increasing the input, you get a different value than when you start decreasing the input in your sequential test. Right? So to avoid that, you can do a random test during your calibration to improve that result. Additional errors that are often reported with different transducers are linearity error, which basically says that the trend that you have over a particular range may be linear, but over a later range is nonlinear. So the difference between the curve fit and the actual data gives you your linearity error. All right. So you can use this equation here to determine the uncertainty in linearity and the percentage of the uncertainty of linearity. So sensitivity error is due to scatter within a data set. So basically the slope could be slightly lower, slightly higher, depending on how much random error you're getting within the measurement. Zero error is due to error in offset in a linear fit. So if you have a y is going to be a function of mx plus b. If you have an incorrect value of b, this leads to issues with, will give you errors in your value of y. Right? And then zero. um, so um, and then um, instrument repeatability would be the ability of an instrument to indicate the same value during repeated independent application of the input. It can be quantified using the standard deviation of those values that you require. Got it. All right. So when we're talking about repetitive measurements, reproducibility is the ability for labs to produce the same results multiple times in similar conditions in different laboratories. So if you were doing the experiment in the Sahara and in Siberia, as long as the labs themselves are at the same temperature, you should still be able to get those same results if you have a reproducible test. All right. Instrument precision is the uncertainty obtained from multiple repeatability tests done on multiple tests on the same model, ideally in different locations. Okay, so that's something that's typically reported with the instrument itself. Overall, instrument error and instrument uncertainty can be calculated by taking by using the following equation here. All right, so this is, you combine all the different errors that we had above. So we had like linearity error, we had sensitivity error, zero error. You could put them all into this equation to calculate the total uncertainty of the measurement. All right. So, and then the last few things we're going to talk about are verification and validation. So verification is just the process of determining if the measurement system and its components are working correctly. This can be done using known inputs and verifying that the output matches the expected value. Validation is validating if the experimental system or simulation itself is correct. This may be done using an other reliable method to evaluate the system. So that would be like something like concomitant methods to validate that the system is truly measuring what you think it is working. All right. Cool. All right. So that finishes this video, and we'll talk about different measurement standards in the next